You need an adapter at all?
No, I have an HDMI.
Okay.
I'm fine.
So yeah, just talking to the gooseneck mic. You're up there, so.
Mhm.
Good. So, but I'm ready whenever you are.
Okay, thank you. Copy and paste this. Whatever. Not very course. I'm gonna post peruse because it doesn't seem like we have a student version.
Okay.
If that's the case, I think we should just post a.
The one that you posted on Discord.
No, I'm gonna just post peruse.
Huh?
I'm gonna post peruse. I don't know what the student version is.
Yeah, but anyway, since there are a couple of students online, we can just give them that.
Yeah, we can just give them the
Yeah.
peruse version as well. I think that we should just go off the peruse version because we don't. There's no student notebook.
Mhm.
We don't have a student notebook.
Actually, just my plan was to delete the encode, decode, like have a class VAE
Mm-hmm.
and then a loss VAE, then to write it.
Mm-hmm.
That's all, yeah.
But I couldn't post anything right now, so I'm posting.
I mean, you could, if you want, you can remove them. And give them this as a student.
Do you want to use ours or the other one? Do you want to use ours or the other one?
What hours?
Our, the notebook that we made or the other?
Okay.
You want to use ours?
Yeah, we can use that. But I mean, we can delete the functions.
There's too many checkpoints. Like looking.
No, no need for the checkpoints. Actually, my idea in this simple one is that they need to understand. You will need to at least
I'm
one.
gonna talking to the gooseneck mic if you're gonna talk to them, because it's like the ceiling mics are kind of hard.
I said I think we can give them like 10 minutes to do it. So
Yeah, just let's give them a notice. So just let's unmute it.
does this work?
Are you plugged in, your laptop plugged in?
No, not yet.
Alright, whenever you wanna plug in, I'll.
So that's when you present screen, right? But does the microphone work? Right?
Yeah, if you want, unless you brought his mic, but, yeah, he's used that one.
Just as a heads up, students, we are currently just releasing a
done.
notebook. So.
Oh, you gotta use the HDMI one.
Yeah.
Yeah. You have an adapter, you said?
Mine's HDMI connected.
I think there is an adapter.
Oh, there, yeah, I don't know where that came from. Alright, you're sharing to the meeting, let's get on the screen. Alright. Oh yeah, you might wanna.
Okay, that's good, because I need.
I extend the desktop on you, but you're ready to go whenever you're.
Wait, just give me a second also.
Yeah, just give me the incomplete one.
I'll just publish that. I have my parts first, just as a heads up.
Yeah, I know.
Okay, so.
I'm just testing one thing. us now, people on Zoom?
They should.
You can probably talk right into the mic.
Okay, can you hear us? People on Zoom? Hello? Are you started?
I'm about to release them.
You don't need to open Zoom on your laptop, it's already on.
Okay, but I don't think they can hear us, no?
Yeah, I think they can, I can hear you, I'm listening to it, but yeah, you don't need to open it on there, it's on there.
Just can we just write to them?
Here, you
Yeah,
can-
we will start in 10 minutes.
You can bring up the chat.
Okay. Thank you.
Can everyone hear us? Check, can someone say if they can hear us on Zoom? I know they can, I can hear.
Okay, fine.
Yeah, but yeah, that's, we're able to see all the chat, so.
Yeah. Okay, folks, and just give us 2 extra minutes, and we will start. Did you upload the incompleted one
Yeah, I sent it to you as well.
on Discord?
Yeah. I'm sorry. Okay. It should be uploaded now. But I edited it. Oh, it's not. It's just. Full. And I will add entries.
Okay, what should we?
Or. Yeah, I actually did post it. Okay. Hopefully they got the also in the book. I'm just gonna double check it's the right one.
Let me switch desktop.
Okay.
Excuse me, but if we need to, I need to drop now this OLAB to the other desktop.
What do you mean, like here?
Yeah. So in this case, what happens is that you can explain on this.
Yeah, so
and
you.
type on this one.
Yeah,
But we can have a solution also on another one.
I could just bring out my computer.
Okay, that's.
That's what I did last time.
Yeah. That would be perfect, actually.
1 sec. I need to find the other one, which is that. My friend, she's not in this.
Is the class actually going on right now?
Oh, it's not really.
What happened?
No one just shows up, that's it.
Okay.
Everybody's through Zoom.
But some people are on Zoom, so we have to give it a.
And it's also recorded.
Yeah.
But like, the recording is not very stringent.
Wait, when are you guys actively on Zoom right now?
Yeah, we are
Yeah.
actively on Zoom. Well, you're not on Zoom, the front of the classroom.
Oh, okay.
Oh, you're just gonna leave now?
No, I'm gonna grab my stuff and come back.
Oh,
Dude, I dropped a shift to come here.
yep.
But honestly, it's really.
Okay, I think I have all the solutions. Why is that imperfect?
I think we're good. If you want to type on mine, just it's all yours.
You. And then, I thought Niti would come and everybody else, but.
Nikki is really
Excuse me,
Paul?
Paul? We just need to put one.
What?
We just need to put this notebook on.
Which, is it through the laptop? It's probably your extended desktop. Go to display section.
I can't display settings. When you need to change it.
Just keep it extended.
No, because extend doesn't replicate it onto the screen.
You just have to drag it over.
I guess the only thing is I don't know how to, I won't be, I would be like,
Yeah, you can just drag it over. You just minimize it and drag it over.
I guess, yeah, just give me a second.
Okay, makes sense. You go put stay on one. Yeah. Desktop. But then what we will do once it's yours. Like give me.
I just put my computer.
Yeah. Because I have a couple of notes.
Are you guys set then?
We are set. We're gonna take like 20 minutes most. If depends. Do we let them? We give them time to do the work, like.
Yeah,
Okay.
kind of.
Okay.
Let's see how interactive
I
because.
go over PCA and stuff like that, and so I'm like, some of the eigen stuff doesn't make sense, but like I have stuff to explain it.
Yeah. Because some people will check it, but if they're not interactive, I thought we would find more people. So we would have asked them to run the thing. But in this case, okay, let's go on, explain the whole thing and yeah.
no pressure, Michael.
There's no pressure at all.
Mostly because I forgot everything.
You're not even, okay.
Hey, I learned PCA last fall.
You did? Good. Good job. This is not PCA. This whole lab is not PCA, by the way. The only thing is it's like the PCA is a prelude to the lab. Hello. Does the Zoom meeting hear me?
No one else is chiming in.
Okay.
But then in this case, we will not give them time to do the thing actually.
You think so? But like, we have to do our 80 minutes, you know?
Yeah, I mean, but we will not pause that much because what I've done actually, I made it like questions and discussions and stop here and stop there. But anyway, let's do it. Okay, we will be the students.
Why is my output?
Awesome. MB. I hope it's okay that I'm watching.
I don't think we literally don't care at all. I think it's actually more helpful because it's 8 a.m. No one's in the company. Okay. What?
You got this.
Okay, well, hello everyone. This is the introduction to Lab 12, which is our autoencoder and VAE lab. So the very first thing that we're going to start on is autoencoders, and autoencoders are very, very interesting. So let's start off with something that's not really autoencoders, which is PCA. So PCA is an unsupervised learning method where we don't really require labels, and it analyzes how data varies and identifies directions. So mainly what I'm trying to get out of here is that we're trying to figure out how we can dimensionalize our data in a lower dimensional form. And so when we do that, we can figure out how we can get the spread of our data. And that's very important because when we get the spread of our data and we can figure out which dimension has a bigger spread and which dimension has a lower spread. That usually correlates very well with classification. So why is this so important? Why is lowering our dimensionality so important?
It's not showing this.
Oh my God, I can't do this.
Okay, just say desktop stay on 1.
Yeah, one sec. Please.
Okay, that's now it shows.
Changes. Okay, there.
Yeah.
So you might be asking us why is it important? So there's 2 reasons why this is so important of reducing dimensionality. The very first thing is recursive dimensionality. So obviously, the more dimensions you go, the bigger space of dimensions you have, and so it's going to be much harder to classify points through that. Like obviously, 3 dimensions, it's much harder to classify a specific point than it is in 1. Another thing is there's a lot of noise with these extra dimensions. So reducing overfit is very important and key. So when do we use it? We kind of use it mainly to lower our dimensionality when we're doing our pre-processing, when we're kind of loading in our data. Okay, let's continue on. So here's a quick example of how PCA works.
So quick question.
Yeah.
Why do we need it? Why do we use it?
Because when PCA lowers our dimensionality, and the reason why we want to lower dimensionality is because there's some dimensions that are very redundant and useless. For this reason, there's a lot of things that we can throw away, and there's a lot of things that are very useful, which we don't really zone in on. And for that reason, PCA really helps us identify which one of those are useful and which one of those are not useful.
Okay.
So a good example is this Fisher iris data set. And so there's only one to-do here because we don't really expect you guys to know a lot about PCA. But if you do a little bit of reading into this, you'll see that there's some eigenvectors, and these eigenvectors will kind of hold what our PCA is. So the top 2 eigenvectors would be the ones in the most left. So all I need to do is modify it. And this will be my first one. Actually, I'll give you guys like a couple minutes, like just 2, and then I'll continue. Is that fine?
Yeah. And I'll keep asking you questions. So you also ask me questions because I have discussion.
Yeah.
So we need to keep it interactive regardless if there is no one.
Yeah, that's fine. Even though I don't know anybody who would be
That much attention.
to be actually I guess 3 is a little not enough though.
But honestly, like it's like even when I worked on it yesterday from scratch, it's amazing, honestly.
I think it's so cool. The only thing I have, let me mute myself.
Okay, I think it's so cool. I think the only issue is it's so like, why do we go from PCA to autoencoders? It's so like, haha, you know, it's just, there it is. Like, we throw I remember one of my professors saying this, it's just like you throw a neural network at anything and it works. And it's like really unfortunate that this works because there is a neural network. In your face.
Okay.
And then we get from, like, we're just getting our dimensionality basically. And then we're getting all the way to our second column. So if we were to get this to our second column and run this, let me just Control Enter. Hopefully this is running. Hopefully it works. This runs on mine, so I hope it runs on yours. Fingers crossed. Why is it taking so long? Does this usually take this long, Masa?
So, because it's still not connected, so it's getting,
Yeah, I know, but
where did you connect this to 800?
no, that it doesn't. I would not assume so. I can connect it to 800. Can I?
Yeah, you should.
I don't know. I don't. I don't know if I have like 2,000 credits on my computer. That's how I run on my.
Oh my goodness.
Okay.
You are not connected to L4. Okay, that makes sense.
Now
Why is it
again.
still connecting?
Like, would you break something?
Oh, okay, this is why. Okay, it should not take that time.
Okay, now it says it exists, right?
Yeah.
Oh my God. Okay, sorry. That was just a typo.
Okay, can you open the notebook settings?
No, it seems like it's fine now.
Okay. Yeah.
But I just did a typo. So unfortunate. Oh yeah, eigenvex, not eigenvex there. Sorry. And so here's what our PCA should look like. So the variance is kind of where our biggest metric is, and the bigger the variance, the more spread out our data is, and it's very important for our data to be spread out, so it's easier to classify. So by order of dimensionality, we sort it right here. We arg sort the best dimensions, and then we get the indexes and everything like that. But as you can see, 0.9 and then 0.05, and then it goes lower and lower. So suppose that I get the last two indexes, and I change the dimensionality there. Sorry, I need to change one number. This needs to go to 4. Our data is really sparse, and it's really hard to classify any of these pieces of data. And that's very important that we need to classify our pieces of data, because this is very helpful for classifying. Let's go back now.
So these represent number of features.
These are the types of features, yes.
Okay.
So like the dimensionality. So it's like the 0 dimension, the first dimension, second dimension, so on and so forth. And so this one's obviously much more classified. So now let's go over checkpoint 2. So what are autoencoders or AEs? So the PCA is sort of an autoencoders sort of encompass PCAs. How that works is that when we're going from the x dimension to the z latent vector, our encoder is transferring the x dimension into a z, usually a smaller dimension. Now, sometimes there's some caveats that happen. Most of those caveats are when you're using an activation function that isn't linear, because up here, as we can see, our PCA is a very straight line. And if we don't have a straight line, that's not really a PCA. It's going to be much more of a nonlinear unsupervised learning method. So that's what's very helpful about our autoencoders, is that we can kind of represent many, many, many more types of lines. So as it says here, it says autoencoder function, the encoder function for our autoencoder maps an input data to a lower dimensional latent space. So it's very similar to what our PCA does. And our decoder reconstructs that original data from the latent space. So kind of given this compressed version of X, we get X hat. So why is that so, like, this is kind of a quick explanation of what I just stated. And as it says, linear AEs. So there's obviously some other forms of AEs that make it nonlinear, and PCA doesn't represent that. So now we're going to be going over a very quick and solid example of an autoencoder. This one has the classic MS mean squared error loss function. Alongside, we're just going to be classifying an image, adding some noise to that image, and seeing if we can kind of retrieve our original image from the noisy image. So let's just go through that. So we have a sequential model. This is going to be much more of a fill in a blank. We'll be going over much more in-depthly of why, I feel like, in the variational autoencoder. But I'll just give you guys like a couple minutes, probably like 3, to just fill it in. I write down each function right next to it, so fingers crossed. Okay, we're supposed to be teaching for 80 minutes, by the way.
How long are you actually gonna teach for?
So what we do, our strategy is that we do like 40 minutes of teaching probably, maybe 50, and then we leave like 2 minutes for the students to do each section of the notebook. But then it's like 2 times whatever, usually at least to 50.
Honestly, it's very, I think the labs are very beneficial for students because, you're technically trying to do the thing in real time.
I'm trying to advertise a course center.
And because, no, seriously, like most of the people, like,
Yeah.
when, for example, for homework or stuff like that, like by default, the first thing they will do, then you go and use AI tools. But in labs, you sit and try to code actually.
I think the labs are a much more easier version of the whole course. That's good. But like,
Yeah.
also, also the lab is 8 a.m.
Seems like a great class, but I don't have the prereqs for this.
If you become you're going to be a grad student this semester, right? So
2 semesters from now.
you could say that you could get the requirements. 'Cause
Really?
The requirements are nothing.
What is it?
0. Zilch. Literally 0 requirements when you're a grad
Wait,
student.
are you serious?
Yeah, when you're an undergrad though, there is requirements.
It's 11,685?
485.
685, 75. 485 is the easiest. But it's 98.
Wait, no, because if I'm a grad student, I have to take the grad section.
Okay, 685 is okay.
Okay.
You would have to have friends.
Ouch. Wait, but I'd be grad in EPP, so it's like, it'd be weird.
Bro, I've had so many grad students from other engineering disciplines.
Yeah.
Oh, so you were a grad student when you took it, right?
Hmm?
Or you're a grad student right now, sorry. I'm going crazy. I might be.
Oh, you're a grad student here?
Yeah, PhD.
I think we took it the same.
Next semester? Did you take it a year ago? Or more?
Yeah. Here we go.
My guy signed me up for the scaffolding version. I was taking the undergrad one, but I stopped that.
So I think you can just start.
Oh, you think so? Okay. Let's just go over kind of just how our denoise autoencoder. So it says the first thing is convolution. So we want to get a 32 by 28 by 28. And we're given a 128 by 128. So we do nn.conv2d. Oh, I can't spell. Okay, there. And it's 1 comma 32 comma. Oops, I literally cannot spell. And then kernel size equals, I think it's 3, and then padding equals 1. Is that right? Yes, okay. And then this is just a row activation function. That's ReLU. Okay. And then, oh, I cannot spell ReLU though. Yep. And then this is a max pool. And then dot max pool 1D or 2D, yes. And then this is going to be just dimensionality of 2. So we just half it. This is another conv2v and then conv2d of 32 comma 64 comma kernel size of 3 comma of 1. And then ReLU again. This is going to take a while. And then that actual.
Brackets and then.
Oh yeah. Oh well, 1 sec. Okay. And then the decoder is going to be like kind of just going the opposite direction. So hopefully you notice that. Also, you're using conv transpose because we're going backwards as well. Conv2d transpose 2d of, and then it's going to be 60. Yes, it is kernel size of 2. Oops. And then,
The previous max pool, what is it?
sorry, what?
The previous max pool? You forgot to mention that.
Sorry, where?
And dot max pool?
I don't believe that this, like, when I was looking at this, it doesn't seem like they use max pool. But yeah, max pool might be helpful. Right.
But I mean, you didn't pass any attributes.
Through it? Oh yeah. Oh, you're right. Can I kick people out of the classroom? Transpose 2D of 132, comma, size of 2 try equals 2, and then dot sigmoid. Okay. And then I'll give you like 30 seconds for the loss. Hopefully you just did a quick Google search on what mean squared error loss is.
So, is there anything you would like to tell us about this loss? Why do we use it?
Specifically for AEs, the mean squared error loss is very useful. I believe I'm not so redundantly clear on why it's used, but I believe it has to do with the fact that we have a denoise output and we're trying to correlate that with our input and see how like similar it is to the actual expected output.
Yeah, technically we need the distance of both of them to be kind
Yeah.
of closer to each other.
And then so this is just and then dot MSE loss. And then I believe that's all. So let me just start running stuff. Hopefully there's no errors.
There's the loader.
Loader's not defined. Why does it work on mine? Wait. Oh, that's a quick error. I believe I might have ran something below.
No, it's up.
Yeah, I know that's the error. I just my computer works. I don't know why.
It should be defined up. So you didn't try it. Go up.
Yeah, one sec. Let me just check. That's like the first instance of loader on my computer, by the way.
I remember you didn't run the data loader part.
I didn't.
No.
Where? Data loader. What? Why does this work?
It's totally fine. This is the point of the lab, to teach people how to debug in real time.
Yeah, real time. Maybe when I'm trying to find it.
Which data set was used for this?
I believe it's just one below. Like I just use your library and then
Ah, okay, you're loading my data set, right?
yeah, probably.
Okay, so go down, then. Go down. Yes, here. Just run it again.
Do you think this will? Yeah, okay.
Yeah, but it just change the name and name it train loader. And then it should be,
It should work.
yeah, it should work.
I believe it's that. Let me just double check that I'm not going crazy and
Yeah, I think it's, you're not going crazy. So just go up and change to train loader in the EQ. Yeah.
score loader. Okay.
Yeah.
It should run really quickly as well, so this is a good sign.
But then there's the length of.
Yeah, loader is not oh, yeah, you're right. Train. Let's go loader. What? Insertion errors. Why are there so many? Let's just see if something happens, outputs something, and if it doesn't, it doesn't. But okay, here's an example. So we have the MNIST data set. We have a bunch of numbers. We put noise on those numbers, and you can see that we have a denoise. So this our input would be these noisy numbers, and we lower the dimensionality. So in our autoencoder. So I'll just explain it. So we have our input, which is our noise. We lower the dimensionality in our autoencoder, so it subtracts all of those dimensions that are very noisy and very redundant and useless. And then we have this latent vector, which is now going to be what we kind of think the most important dimensions are for our like number. And then we use our decoder to get the most important dimensions from our number to bring it back to a representation that has no noise. And obviously you can see that there's a little bit of like blur. If I train this for example, let's look at the 6, there's a lot more blur on this 6 and this 2. And so there's some limitations with just having a regular autoencoder. So obviously one thing is that we can still like overfit very in-depthly just because we don't have a lot to work off of. Our latent space goes down to one number and then it goes up. But if we keep on training on the same data set, we're gonna kind of memorize which number we're supposed to go up from, or which number we're supposed to be decoding from. So there are a lot of limitations when it comes to generating alongside that. Another thing is that there's you only can have so much for your latent space because you only can have up to one like nonlinear line, as there's only a latent vector. There's not multiple latent vectors. And so obviously now, speaking of that, there's going to be ways to overcome these limitations, which this is where variational autoencoders come into play. And so Masa will be going over what variational autoencoders are.
Great.
And
Ask the question, sorry, but pay attention. Yeah. One for 1 second, and I'll try to do something like no. It should cheat the question.
I'll use one.
Send it to
I'm gonna go to I don't know what the
Can you just also open this?
Yeah, I can have this on my. Yeah. There.
Yeah.
Do you want like this?
Do you want me to download it? Do you want it like this or me to download
No,
it?
no, no, it's good. That would be.
Do you want me to split?
Or just down. Yeah, keep them like this. That would be really nice.
Like something like this?
Yeah, that would be perfect. So I'll continue now on the VAE, which is the variational autoencoders. Share to meeting. Okay. So here we will understand like what is the VAE and how it's really differing from regular autoencoders, and we will implement a simple VAE, and you will realize that the example that we will implement is super simple, and the idea is actually to understand what is the real purpose of a VAE, and then we can keep improving on top of it until we get better results. So the difference between the autoencoder and the VAE, so in the autoencoder, actually, you encode to a single point in the latent space, but VAEs actually encodes into a probability distribution. So the encoder outputs the mean and the variance in the latent space, and and encode to a probability distribution. So this thing will allow what? This thing will allow the generation and the sample from this distribution to get the latent representation. So like the best part about it that we can generate actually new samples by sampling new data by sampling from the learned distribution. Why do you think this is useful? Why do you think, Mike, do you have any thought?
So we can like predict examples and generate more better.
Amazing. Any thoughts? Okay, so actually, even though they're written here, so so the first thing, it's like a generative model. So you create new realistic data samples. You smooth the latent space, so similar inputs produce similar latent codes, and uncertainty. So the model can express uncertainty in its encoding. This is also kind of really cool. So I will have one thing to start with. I will start with coding the thing. So what we will use for today is the Menace dataset. Who knows what's this dataset?
It's a 28 by 28 data set.
Naturally.
Is it an image data set from numbers?
Exactly. So it's like technically it's a handwritten data set images. So and so the 28 times 28 is the resize that we did as a pre-processing part. So let me start. We will start working on the code, and we will import important libraries. So someone would say, oh, but this data set is kind of really is simple. Yeah, so the idea is that we need to do the thing on a simple data set and make sure that we can achieve that. And then later on, we can just replace it with any data set we want. So again, here, we're converting to tensors. We're normalizing to 0, 1. And one thing is that this is in a grayscale. You can change the batch size according to how much memory you have and on what type of GPUs you're. But anyway, like most of our students, they have the 800 by default from Colab. So I will be here just visualizing some examples to show our data set. So these are images from our data set. And now we will build the VAE. So the first thing, I have the input dimension, which is the size of the flattened input. Okay? And the second thing, so I assigned this self.input dim equal input dim, and the latent dimension, which you would realize it's a very important thing. It's the number of features, and we can keep playing with it to see how could this affect the performance of our model. And the other thing is the following. So I will need, first we need to map the input to a hidden representation. So what we will do is, I will do something very, very simple. I will not put any convolution. Just let's say dot fc1, like as of a fully connected, and then we can say just a simple linear layer where it maps the input dimension to a hidden dimension. Then I need now the mean. So the mean is the self dot fc mu, which equals to nn dot linear dot the hidden dimension, comma, the latent dimension. Now I will need also the variance. Okay, my question is to you is the following. So for the variance, what should I actually get as an input? What should be the, sorry, the n dot linear? What should I be mapping? What should I be really mapping? So for the input, I'm mapping the input dimension to the hidden dimension. For the mu, I'm mapping the hidden dimension into the latent. How about the variance? Actually, it's exactly the same. So we need also to map this. Okay, this is for the encoder. And for the decoder part, I will also need another fully connected layer and n dot linear. And now I want to go back. So I want to go back from the latent dimension into the hidden dimension. And here, for the last one, I'm mapping actually the hidden representation back to the input space. So let's say FCC, and then we can say hidden dimension into the input. So maybe like your question would be, like, isn't that too simple? Like linear layers, can we replace them with something more powerful? What can we replace them with?
Like an activation function or something?
And also, like as you showed in your example, we can also use convolutional neural networks instead of just simple linear layers. But the idea here also to make it run technically fast. So in the encoding part, what should we return? Like when I encode, what am I expecting? I'm expecting to get the mean of the latent distribution and the log variance. So I need to encode them. So what I need to add actually is the following. We just say h equals f dot relu, and then I just call the fc1 and I pass the x. This is our hidden representation. And now when I need to get the mean, which is the mu, I just say self dot fc mu, and I pass the h. Now for the log variance, I just pass the log variance and I say self log var. Then I put the h. And in the return, what should I return?
Both mu and the log variance.
Exactly. Both the mu and the log variance. So this is actually really important because like when we return this, let me just 1 second. Now for the most important thing, and I added the formula here, which is the reparameterization trick. So why do we need actually reparameterization? Is it really like important to have this? So think about this as if we're playing darts, okay? And this epsilon, which is the random sampling, as if I'm just throwing darts without any kind of learnable parameters. But in the reparameterization, we would have two learnable parameters. As you can see here, we would have the sigma and the mu as our learnable parameters. So I will do the following here. So in this case, when for example, I'm throwing the dart and I have learnable parameters, let's say if the random noise was the wind, if we need to think about it, and I'm throwing the darts, and then if you think about the sigma as if like, okay, go left or go right, and these parameters are being learned, so we can technically backpropagate. The gradients can flow through this. So this is the kind of the most important thing in the in uh, in the um, in the VAE. So first step, actually, we need to get to compute the standard deviation, which is torch dot x 0.5 dot log variance, and then the epsilon is just a random, and then the z equal mu plus std times epsilon, and this is the reparameterization that people most of the time get really scared of. So again, without this reparameterization trick, you would be technically, you can't backpropagate through just randomness. And so is it clear or not? Is it clear?
Like, you need to explain why the randomness. Like, why do we use randomness? Like, why do we have to throw the dart? Why can't we just get like an input representation, pass it through, see like the mean, maybe from like the whole distribution set or whatever, and do it that way?
So the thing is like,
Why do we even need the randomness?
Yeah.
Why do we need the noise?
Like, yeah, exactly. What do we need the noise?
So here's the thing that like our objective invokes like a denoiser reconstruction loss. So what you need to actually do is that when you have these, like let's say, when you start with this input, you're trying to denoise, and when you add this noise, you're trying to make sure that you're kind of learning how to retrieve or sample from this latent space. So I think now we need to start to look into the decoder, and then we will start working on the loss, which will make things kind of more clear. So for the decoder, first of all, we just pass the relu self.fc3, the z, which is the latent code. Now we have the code. From that code, we need to reconstruct. And the reconstruction equal torch dot sigmoid self dot fc4, and then we pass the h, and then we return the reconstructed image. Now for the forward, like the forward, you technically just flatten the input. You just use the self.encode. You sample from the latent distribution. So technically, the reparameterization is the portion where you sample from the latent distribution. And then you do the decoding part. So let's run this. Okay. So look, here I said that the input dimension is 784, which is because our image is 28 times 28, so the flattened version is 784. And then we chose like hidden dimension, which is 400, and we chose the latent dimension, which is 20. And then we run this. Now going to the loss. So how well can we reconstruct the input? In this case, we will need a loss. We can use the MSE loss, which is actually also very like kind of more famous in these problems. But also since we're here working on pixel-wise comparison, we can use the binary cross entropy to get the value of the brightness, which is technically between 0 and 1. And whenever it's lower, then we have a better reconstruction. And the second function that we should use is the KL divergence. And for the KL divergence, it's actually, it measures how far is our encoding from the standard distribution. And this is the most important thing. And then you can definitely sample from the standard distribution to generate new data. And it also regularizes the latent space. So actually, if we need to think about the intuition behind this, it's like keeps the latent space kind of more organized. Because you don't want to go into a latent space which is like kind of like noisy. You need it to be more meaningful. So we will write these the reconstruction loss, which is here the the binary cross entropy. Comma x, comma the reduction equal the sum. This is this one. So my question is, can we eliminate any of these losses? Can we say, okay, like I don't need this? Can I just, for example, like put only the reconstruction loss? Actually, no, the thing is like if you just kept the reconstruction loss, the encodings are going to spread randomly and you can't really generate. And if you kept the KL divergence, actually, everything collapses to the same point. So you actually can't reconstruct. And so together you get the organized space and a kind of good reconstruction. So for the KL loss, you can say minus 0.5 times the torch dot sum 1 plus log variance mu dot pow 2, and then the total loss is actually the reconstruction loss plus the KL loss. Now for the training, again, like I would like to plot our the results and stuff like that. Okay, let me check what's wrong. Oh, okay. I was putting binary cross entrop instead of entropy, which is okay. So I'll have to just rerun this and run this. Okay, have something else. Okay, using a target size, torch dot size 120. That's different to the input size, which is 128. Please ensure they have the same size. Let's go back and check. Okay, so here I should put actually dot view, which makes a lot of sense actually. So they can match with the size. Okay, going back here. So that, you know, that's the good part when you have a small network, you can okay, I have one thing in the KL divergence. I forgot one attribute. So which is minus the log var dot exponential. 0.5 times torch 1 plus log dot var. Okay. Because it immediately showed when I got negative KL divergence. It's not, doesn't make sense. Because the KL divergence should be like kind of moderate. And also I'll give some time for students to like code the VAE class. Just maybe 5 minutes. Let's plot the training curves. Look these training curves. Reconstruction, KL divergence. Let's visualize the reconstruction. Look.
Like they're kind of okay.
But if you need things to be like, so for like even these are good like even though they're but I think we need to use also convolutions. We need to use more powerful things. But anyway,
Realize that the VAEs
in general they'll produce blurry results. And this is what we will address on Monday, which is in the diffusion, which we address these issues. But I'll give now 5 minutes
for students too.
I was watching the video and at a point I did and I was like, it always ends up here, isn't it? So I started laughing because like I started going over elbow and everything like that. It was entertaining for a while. Because I was like, I'm just here to learn about VAEs. Why are you going over elbows?
Okay. Okay, one question. What could happen if we, okay, let's first visualize these. What could happen if we technically changed the number of the latent dimensions, like from 20 to 2, stuff like that? What could happen?
Our data would be more or similar.
So actually, if you change it to 2, you would get high compression. Your model will train faster, but you will get more blurry results. Let's say if you put something like around 20 to 50, you can kind of get good quality. It could be more balanced. And for this data sets, it's like kind of reasonable. but if you, let's say, put like 128 and more, you will get like way more better quality, but the compression would be lower. But this will take like more time in the training. Now I was just trying to see like what if we did interpolation, which is kind of smoothing transitions between images. And this thing will actually tell you how good is your latent space. And are there many spaces or noise in it? So it's also like something just very cool to try when you're doing things in the latent space. So for example, if I'm interpolating 2 and 5, what could I get? So okay, let's run it multiple times for different things. So this shows you your latent space and the quality of it. So first of all, the key takeaways from this, what we've learned is that we've learned about the encoder and what we really need to return, and why is it important to also to return. Also, you're returning also the uncertainty, which is kind of good. We talked about the reparameterization trick for backpropagation. We coded also the decoder for the reconstruction. We coded 2 different losses, one to reconstruct the input images, for reconstruction loss, and the KL divergence. Again, we said that for this specific case where we're working on a grayscale and we have this, using the BCE was a good decision. Can we use the MSE? Yeah, definitely. And it's actually more used. And what I would like students to do, like offline, is actually to try different latent dimension and play with the interpolation to really understand the latent space there. Like, because for example, if you find, like, let's say blank spaces in the latent space, or you will get like kind of garbage images. So this will just also, you will be literally visualizing your latent space. But you can definitely change the loss to MSE and try how things are going. Apply to different data sets. There are also existing data sets in Torch library, which is like you don't need to change much. Now, like for example, you can just replicate this and like change the latent space into 2, but you need to change it from the very beginning, from here, where you just change it and you just start seeing the quality. You will see that the quality will get worse. So this is a good exercise to also try. One more thing, can we control what digit is generated? Is that possible? Yes, with conditional VAE. So technically that's our lab so far. If students have any question, they can post on Piazza, on the lab post, and I think we will not provide the solution notebook. Yeah, so because they can just follow the lab and follow the YouTube video for this.
I think a lab is so important, that the students will just deduce everything, so.
Okay, thank you everyone, and see you hopefully on Monday.